Welcome to The Explainer. Today, we're going to dig into a concept that is absolutely fundamental to how the internet scales without, well, collapsing under its own weight. It's called consistent hashing, and honestly, it's the secret sauce that lets your favorite services grow from a few users to millions, almost overnight. So let's kick things off with a scenario that, if you're lucky, you'll face one day. Your app is a total hit. Requests are just flooding in, and your one little server can't keep up anymore. The obvious move? Add more servers. Scale out. But here's where things get tricky. There's a hidden trap. If you distribute all that work the wrong way, the very act of adding a new server, the thing that's supposed to save you, can actually trigger a catastrophic failure across your entire system. Okay, let's get into it. To really appreciate the solution, we first have to understand the problem. So let's look at the simple, intuitive approach that gets so many people into trouble. How do we balance the load in the first place? Well, the standard way is pretty straightforward. Every request has some kind of unique ID. We take that ID, run it through a hash function to get a big number. Then, we use the modulo operator. Now, that's just a fancy term for getting the remainder after division. You take the hash, divide it by the number of servers you have, and the remainder, 0, 1, 2, or 3, tells you exactly which server gets the request. Simple enough, right? And you know what? This works beautifully at first. Because a good hash function spreads its results out pretty randomly, every server gets a roughly equal slice of the pie. If you've got 4 servers, each one ends up with about 25% of the traffic. It seems like a perfect system. But now, the crisis hits. Your service is still growing. You have to add another server to keep up. So you go from 4 servers to 5. The second you add that 5th server, the number in our little formula changes. We're not dividing by 4 anymore, we're dividing by 5. And here is the absolutely catastrophic part. This doesn't just affect new requests. The result of that formula changes for almost every single existing request in your system. Now, let's think about why this is so bad. A lot of the time, you use this hashing to figure out where to store a user's data. In a cache, right on the server. That way, you don't have to hit your database every single time. But after this system-wide reshuffle, almost every user is now being sent to a new server, a server that has no idea who they are and doesn't have their data cached. The result is a total system meltdown. Your caches are instantly worthless. Every server is flooded with cache misses, which unleashes a massive storm of queries on your database, which can easily bring the whole service crashing down. And all this happened because you tried to add one more machine. So, how do we fix this mess? The solution is just elegant. We change the way we look at the problem entirely. We stop thinking about our servers as a numbered list and start thinking about them as points on a circle. Welcome to the hash ring. I want you to picture this. Just imagine a big, continuous circle that represents every possible value our hash function can spit out. Now here's the really cool part. We map everything onto this ring. We don't just hash the requests. We take each server's ID, like its IP address, and we hash that too, to give it a place on the ring. Then we do the same thing for every incoming request. So now our servers and our data are all living in the same space. And the rule for figuring out who does what? It's beautifully simple. You find where a request lands on the ring, and then you just travel clockwise until you hit the very first server. That server, that's the one responsible for this request. And this is where the pure genius of the hash ring really shines. Let's see how this new model handles those exact same scaling problems that totally broke our old system. All right, scenario 1, disaster strikes. Server S1 crashes. It's gone. It disappears from the ring. What happens to all the requests it was supposed to be handling? Well, with our new clockwise rule, those requests aren't lost. They just keep going. They travel around the ring until they hit the next server in line, which is S4. And here's the magic trick. Servers S2 and S3 are completely unaffected. They have no idea anything even happened. The disruption is totally contained. Okay, now for the happy scenario. We need to add a new server, S5, to handle all our new traffic. We hash its ID, and bam, it lands somewhere on the ring. So what happens now? The new server, S5, simply takes ownership of all the requests that fall in the gap right before it. This means it only takes work away from its one single immediate neighbor. Again, the rest of the system is completely untouched. Almost all of our precious cache data is still valid. The disruption is minimal. But, it's not quite perfect yet. There's one more problem. Since we're placing servers on the ring randomly, what if they all just happen to clump together in one spot? Then one poor server could get a huge chunk of the ring, while another gets almost nothing. We call this a hotspot. And the solution for this is a really slick engineering trick called virtual nodes. Instead of putting each physical server on the ring just once, we basically give it a bunch of aliases. We use a few different hash functions to place it on the ring multiple times. So server 1 might show up as S1-A, S1-B, S1-C, and so on, all around the ring. By doing this, by representing each real machine with maybe hundreds of these virtual points, we dramatically smooth out the distribution. It's just the law of large numbers kicking in. It makes it way more likely that the load on each physical server is going to be balanced. And this is why this whole thing matters so much. This isn't just some abstract computer science theory. It's the invisible engine powering huge chunks of the modern internet. We're talking massive distributed databases like Cassandra and Riak, huge caching systems like Memcached, and the content delivery networks that are probably streaming this to you right now. You see, in the end, consistent hashing teaches us a really profound lesson about system design. Building something that can scale isn't just about throwing more powerful hardware at a problem. It's about designing a system that can gracefully adapt to growth, to failure, and to change, all with the absolute minimum disruption. It's about building for resilience right from day one.